somewhere in the dark between constellations, a single star glows with such absurd width that light traveling at 186,000 miles per second needs more than 9 hours just to cross from one side to the other. If you swapped it for our Sun, every planet you have ever heard of, Mercury, Venus, Earth, Mars, Jupiter, Saturn, would vanish inside it. Not orbit it, not be incinerated near it, vanish inside it, swallowed without leaving a ripple in the outer atmosphere. We are going to travel through the full catalogue of these objects tonight, from the familiar stars that have guided human navigation for thousands of years, all the way to theoretical giants so vast that entire solar systems would disappear inside them, like grains of salt dropped into a swimming pool. Some of what we are heading toward should be impossible under the laws of physics as currently understood. Some of the stars on this list have already died, and we do not know it yet because the light from their deaths is still crossing the gap between them and us. Stay close. The scale of what actually exists in this universe does not fit inside normal language, but we are going to try anyway. Step outside on a clear afternoon, and the answer seems obvious. The Sun is enormous. It spans roughly 865,000 miles across. You could line 109 Earths side by side across its face and still have room. Pack it hollow, and you could fit more than 1 million Earths inside before running out of space. Standing on this planet, these numbers carry a kind of finality, as if they mark the outer boundary of what large can mean. They do not. Among the full census of stars distributed across the observable universe, our Sun is ordinary to the point of being forgettable. Picture every beach on Earth, every grain of sand on every shore. Let each grain represent one star somewhere in the universe. Our Sun would be one of the smaller grains, slightly below average, surrounded on all sides by grains the size of pebbles, then marbles, then bowling balls, then objects the size of cars, and then buildings. The beach goes on further than you can see in any direction. We live around an unremarkable grain. Astronomers measure stellar size using a unit called the solar radius. One solar radius equals the distance from the center of the Sun to its surface, roughly 432,000 miles. When a scientist describes a star as being 1,0 solar radii wide, the meaning is that a straight line from one edge of that star to the other would span our Sun's diameter 1,000 times. Over. The largest confirmed star known today pushes past 2T100 solar radii. Place it where our Sun sits and its surface would extend past the orbit of Saturn. Not to Saturn's orbit, past it. Everything inside that radius, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, would be inside the body of the star. Placed beside our Sun at accurate scale, our Sun would be a pinhead next to a basketball, and even that comparison flatters the relationship. Every star is fundamentally a machine for maintaining a single balance. Gravity pulls every atom of the star inward toward the core, compressing everything with a force proportional to the star's total mass. Nuclear fusion in that core generates a continuous outward flow of energy, photons, radiation pressure that pushes back against the inward pull. When these two forces match exactly, the star holds its shape and burns steadily. Our Sun has maintained this balance for nearly 5 billion years and should continue for roughly 5 billion more before the hydrogen fuel in its core runs thin. When that happens, the core will contract, the outer layers will expand dramatically, and the Sun will swell into a red giant large enough to engulf Mercury, Venus, and possibly Earth before finally shedding its outer layers and collapsing into a compact white dwarf. Gradual, slow, ultimately quiet. The death of a patient star. The stars that dominate this journey do not die quietly. They are too massive for patience. Their cores run hotter and denser than anything in our Sun. Their fusion rates are orders of magnitude higher, and they exhaust their hydrogen supply in a few million years rather than 10 billion before swelling to the monstrous proportions in this catalogue. As they grow, their outer layers become increasingly loosely held. Material bleeds continuously into surrounding space. They pulse and convulse and change shape from month to month. They behave less like stable spheres and more like vast unstable storms that happen to be roughly spherical. Each one is racing toward a specific kind of end, an explosion that briefly outshines the entire galaxy containing it. These are the objects worth understanding, because understanding them means understanding where everything you are made of actually came from. Before we meet the monsters, a word about the light we use to observe them. The light leaving a star 640 light-years away takes 640 years to reach your eyes. The light from a star 5, 0 light-years distant, has been traveling since before any recognizable civilization existed. When you look at one of the giants in this catalogue, you are not seeing the star as it currently is. You are seeing it as it was, often long before anything resembling recorded history, sometimes long before our species existed at all. For some of these objects, the explosion has already occurred. The death is already in the past. The light from that death is already moving toward us through the dark, traveling at 186,000 miles per second, due to arrive some ordinary night without any warning. The star you see glowing in the sky tonight might be a ghost, a memory of something that no longer exists. The night sky is not a picture of any single moment. It is a composite of thousands of different historical eras, each object seen at the epoch corresponding to the time its light left it. Sirius shows you light from less than a decade ago. Betelgeuse shows you the year 1385. Stevenson 218 shows you the last ice age. Every direction you look is a different moment in the past. The brightest star in the night sky has been deceiving observers for at least 5,000 years. Sirius burns in the constellation Canis Major with an intensity that made it sacred to ancient Egyptians, who timed the annual flooding of the Nile by its heliacal rising, the moment each year when it reappears before dawn after a period of invisibility. The appearance of Sirius told Nile Valley farmers that the flood was roughly 70 days away, giving them a predictable agricultural lander in a landscape where that calendar was the difference between civilization and starvation. Polynesian navigators in the Pacific used it to steer across hundreds of miles of open ocean without landmarks. Mesopotamian astronomers included it in the earliest star catalogues. Greek writers called it the scorching star and attributed summer heat waves to its influence. Everyone assumed that something burning that ferociously in the sky must be enormous. Everyone was wrong in the most instructive possible way. The cultural weight carried by Sirius throughout human history illustrates something profound about the relationship between skywatching and civilization. The Egyptians who built their calendars around Sirius were practicing a form of applied astronomy sophisticated enough to coordinate agricultural activity across an entire river valley civilization. The temple at Karnak was oriented so that the rising sun on certain days of the year would illuminate specific interior chambers through carefully aligned doorways, and those alignments involved Sirius as a reference point in the long-range planning of the temple's construction. This was not superstition. It was engineering based on careful observation extending across generations. The fact that Sirius turned out to be physically unexceptional when finally measured does not diminish its role. It was precisely close enough and bright enough to function as a reliable annual marker, and its use for that purpose produced genuine civilizational value across multiple cultures simultaneously. Sirius sits approximately 6 light-years from Earth, making it one of the closest stellar neighbors we have. Its spectacular brightness in our sky has almost nothing to do with its actual size, and almost everything to do with its proximity. When astronomers finally measured it properly, Sirius A turned out to be roughly 1.7 times wider than our Sun, a modest upgrade, barely a footnote in a catalogue of giants. The lesson this delivered to early astronomy was the most important methodological insight the field ever had to absorb. Apparent brightness in the night sky tells you almost nothing meaningful about a star's true scale. A flashlight pressed close to your face looks brighter than a stadium floodlight across a parking lot. The sky plays this trick continuously on every observer who does not already know to correct for distance. Sirius was the most famous victim of this illusion for thousands of years, and its unmasking changed how the science was done. What made Sirius scientifically transformative was not its size but its companion. In the 1840s, German astronomer Friedrich Bessel noticed that Sirius moved through space with a subtle wobble in its path, the kind of wobble that only one thing produces, an invisible gravitational partner tugging on it from the side. he predicted a companion star that no instrument of his era could resolve directly. 2 decades later, improved telescopes finally caught the culprit. The companion, now called Sirius B, turned out to be something genuinely strange. An object approximately the size of Earth that nonetheless contained nearly the full mass of our Sun. A teaspoon of its material, brought to Earth's surface, would weigh several tons. This was the first confirmed white dwarf, the collapsed remnant of a star that had burned through its fuel and been compressed by its own gravity into an object of extraordinary density, no longer generating energy, simply radiating away the heat of its formation. When a star exhausts its nuclear fuel and sheds its outer layers, what remains is the core. Carbon and oxygen nuclei surrounded by a sea of free electrons held up by electron degeneracy pressure, a quantum mechanical force that has nothing to do with temperature and everything to do with the fundamental rule that no two electrons can occupy the same quantum state simultaneously. A white dwarf does not burn, it simply cools over billions of years toward darkness. Consider what the existence of Sirius B implies about deep time. Before humans walked upright, Sirius B was likely the more impressive member of that stellar system, larger, brighter, hotter, burning through its fuel faster than the dimmer companion orbiting beside it. It ran through its hydrogen supply, expanded into a giant, shed its outer layers in a phase that would have been spectacular from nearby, and collapsed into the dense cinder that now orbits Sirius A. The material that explosions scattered into surrounding space eventually became part of the interstellar medium, mixed with other gas and dust, and contributed to the clouds that would later form other stars and planets. Sirius A will follow the same path eventually. Our own Sun will follow it. The difference between the stars we are about to visit and stars like Sirius is not in how they live. The same fusion, physics governs all of them, but in how they end. The modest ones die with a sigh. The massive ones die in events that reshape their neighborhoods. Look up at Orion on any winter evening. Most eyes find the 3 belt stars first, then trace outward to the 2 bright points at the shoulders and the 2 at the feet. The sharp blue-white point at his right foot has been visible to every human who ever looked at a winter sky, and it is not what it appears to be. Rigel. The light now arriving at your eyes from Rigel left that star around the time the Black Death was moving across Europe, killing a third of the continent. Despite that journey of 860 light-years, Rigel still ranks among the brightest stars in the entire night sky, which means its actual physical output must be extraordinary to remain so, visible across such distance. Rigel measures approximately 78 times wider than our Sun. If our Sun were removed from the center of the solar system and Rigel substituted in its place, Mercury would be inside the star, Venus would be inside, Earth would be inside. The sky from where Earth's orbit once was would not look like a daytime sky. It would be the interior of a nuclear furnace. Rigel generates roughly 120,000 times the total energy output of our Sun every second, and it does this at a surface temperature of around 20,000 degrees Fahrenheit, which is why it burns with that precise, cold, blue-white color. In stellar physics, color and temperature carry identical information expressed differently. Red means cool, orange means cooler than average, yellow means intermediate, white-blue means very hot, blue means extreme. Rigel is one of the blue elite, burning at temperatures that place it among the hottest stellar surfaces in the catalogue. The blue supergiants, like Rigel, represent one end of a spectrum in stellar evolution that connects directly to what we see in the red giants later in this catalogue. A massive star begins its life burning hydrogen in a hot, compact blue state. As it ages and its hydrogen is consumed, the core contracts and the outer layers expand and cool. The star transitions from blue to yellow to orange to red as it grows larger and cooler. Rigel may itself eventually swell into a red supergiant before exploding, though the details depend on its current mass, rotation rate, and internal structure. Some blue supergiants explode before reaching the red supergiant phase. Others make the full transition. The supernova of 1987, called SN 1987A, which occurred in the Large Magellanic Cloud and was the closest supernova observed with modern instruments, came from a blue supergiant rather than a red one. Its light curve behaved differently from what models of red supergiant explosions predicted, leading to significant revisions in stellar evolution theory and demonstrating that the picture of how massive stars end is richer and more varied than any single evolutionary track. The blue giants burn through their fuel at a rate that makes their lifespan laughably short by astronomical standards. Our sun has been running steadily for nearly 5 billion years with an equivalent amount of time remaining. Rigel is only around 8 million years old and is already in the final stages of its hydrogen budget. In cosmic timescales, 8 million years is a rounding error. Astronomers estimate the star will detonate as a supernova within the next few million years. When it goes, the explosion will be visible from Earth in daylight. People on whatever version of this planet exists at that point will see a new star appear at Orion's foot, bright enough to cast faint shadows at night, bright enough to see clearly at noon, fading over weeks and months before the constellation loses one of its defining points of light permanently. Rigel also conceals something most skywatchers never know. It is not a single star, but at minimum 3 locked in a gravitational configuration, possibly 4, with smaller companions orbiting the massive primary at distances that keep them unresolvable without a substantial telescope. The word soon in astronomy means something quite different from its everyday usage. When astronomers say Rigel will explode soon, they mean within the next few million years. By human standards, a million years is essentially infinity, and yet, against the background of the galaxy's 13 billion year history, a few million years is indeed brief. Rigel joined the main sequence only 8 million years ago. The galaxy was already more than 10 billion years old when Rigel was born. The star will live its entire existence in a sliver of cosmic time that most other stars currently burning will barely notice has passed. The color distinction between Rigel and the stars that follow is not cosmetic decoration. It encodes a fundamental physical difference in what each type of star is doing. Blue stars are compact and burning fast. High surface temperature, high energy density, all of it crammed into a relatively modest volume. Red stars have expanded so dramatically that their outer layers have cooled to a fraction of their original temperature, even while their cores may be fusing increasingly heavy elements at ferocious rates. That deep red color is the visual signature of a star in the late chapters of its life. The physics producing that redness is the physics of an ending in progress. Turn to the other end of Orion. The orange-red ember glowing at the hunter's shoulder is one of the most closely monitored objects in observational astronomy, and for good reason, Betelgeuse. The name arrives from Arabic through a long chain of mistranslations, and the result sounds faintly undignified for one of the most extraordinary objects in our stellar neighborhood. What it refers to is a red supergiant sitting approximately 640 light-years from Earth. Close enough to study in detail, large enough that the details it reveals are genuinely alarming. The physical dimensions of Betelgeuse resist comfortable absorption. The star measures roughly 764 times the width of our Sun. Place it at the center of our solar system and walk through the consequences. Mercury is gone, consumed inside the stellar body. Venus is gone, Earth is gone, Mars is gone, the asteroid belt is gone. The outer atmosphere of Betelgeuse pushes to somewhere near the orbit of Jupiter. Our planet would not be exposed to intense radiation from outside. Our planet would be inside the star, vaporized long before it reached the core. Betelgeuse is not an object you orbit. It is an object you would be inside. Betelgeuse is not quiet. Its surface churns with convection cells, enormous bubbles of superheated gas rising from deep in the interior, breaking through the outer surface, radiating energy, cooling, and sinking back down as new material rises behind them. In the Sun, convection cells are roughly the size of Texas, millions of them tiling the solar surface, each one rising and falling over a few minutes. In Betelgeuse, only a handful of these cells cover the entire stellar surface at any given time, and each one is comparable in scale to the entire orbit of Mars. A single convection cell rising through Betelgeuse and breaking the surface would transport more energy during that transit than the entire Sun radiates in a year. These cells rise over months, remain active for years, and sink back over similar timescales. The asymmetric heating they create drives the irregular pulsations, the variations in brightness, and the violent episodic ejections that characterize the star. The Great Dimming of 2019, when Betelgeuse fell to 40% of its normal brightness over a few months, was eventually traced to a sudden massive ejection of plasma that condensed into dust and blocked the outgoing light. It was not the star preparing to explode. It was the star demonstrating exactly how violently it can shed material in brief episodes rather than in a smooth, steady wind. The Hubble Space Telescope was pointed at the star during the dimming and returned images, showing that the southern hemisphere had darkened dramatically while the northern remained relatively bright. A clearly asymmetric pattern consistent with a localized ejection rather than a global pulsation event. As the dust dispersed over the following months, the star's brightness recovered. What the event demonstrated is that Betelgeuse is capable of sudden, large-scale ejections of material that temporarily obscure it from distant observers. Each such event is a symptom of the star's increasing instability as it approaches its end. Eventually, one of these symptoms will be the terminal event. The fact that Betelgeuse is one of the closest red supergiants to Earth makes it invaluable as a scientific subject. Most red supergiants are too far away to study in any detail beyond basic spectroscopy. Betelgeuse, at only 640 light-years, is close enough for interferometric imaging, the technique of combining light from multiple, widely separated telescopes to achieve angular resolution far beyond what any single instrument could reach. The first crude resolution of Betelgeuse's disk in 1996 by the Hubble Space Telescope marked the first time any star other than the Sun had been seen as a disk with visible surface features rather than a point of light. Since then, the images have improved dramatically. Modern interferometric observations have tracked individual bright spots, giant convection cells rising and sinking across multiple seasons. The asymmetric shape of the star's extended outer atmosphere has been mapped. The dust that formed during the Great Dimming has been imaged directly. Betelgeuse has become a real, three-dimensional object in our understanding rather than just a set of numbers in a catalogue, and the data it continues to provide about the physics of massive red supergiants is available from no other source at comparable quality. The end for Betelgeuse is not uncertain in type, only in timing. The star will detonate as a supernova. That is as close to certain as astronomy gets. The uncertainty is whether the explosion occurs tonight, next decade, or 50,000 years from now. In the context of stellar evolution, these possibilities are all described by the same word. Soon, when it goes, Betelgeuse will briefly match the brightness of the full moon. It will be visible during the day. At night, it will cast distinct shadows. The show will last weeks before gradually fading, and when it is over, the shoulder of Orion will be dark permanently. The haunting truth is the light delay. Whatever is actually happening to Betelgeuse at this moment will not be visible to anyone on Earth for 640 years. The explosion may have already occurred. None of that information has reached us yet because nothing carrying that information can travel faster than light. Every night that Orion rises, the shoulder that glows there was generated 640 years ago. The star you see might not exist anymore. Drag your gaze south towards Scorpius. Its brightest star burns with a deep, unmistakable blood-red colour, and its name comes from the competition it presents to observers. Antares, rival of Mars, named because ancient skywatchers kept confusing it with the red planet. There is nothing Martian about it. Antares is a red supergiant roughly 550 light-years from Earth, and its dimensions make Betelgeuse look restrained. It measures approximately 700 solar radii across. Place it where our Sun sits, and its surface pushes past Mars and reaches toward Jupiter. The asteroid belt dissolves into the stellar body. If our Sun is a baseball sitting at one end of a football field, Antares is the entire stadium. Every seat, every corridor, the parking structure outside. This is not a metaphor chosen for drama. It is an attempt to make actual proportions communicate at a human scale. Antares burns at roughly 6,000 degrees Fahrenheit on its surface. Cool for a star, which is why it looks red. The physics connecting stellar temperature to colour follows directly from the same principles governing any glowing object. Lower temperatures push emitted light toward longer wavelengths. Longer wavelengths mean red light. Antares is not red because it is dying in any simple sense. It is red because its outer layers have expanded and cooled as the internal fuel situation has shifted. Deep inside, its core is fusing progressively heavier elements, each stage releasing less energy per reaction than the one before, each stage buying less time, the timeline accelerating toward the iron that will end everything. The star has a companion, a smaller hot blue star called Antares B, orbiting at a distance comparable to our Sun's distance from Pluto. From any sky closer to the system, the combined illumination of one enormous red sun and one small blue point would tint shadows a faint purple. Whether any planet in that system could sustain stable conditions long enough for complex chemistry is a different question entirely. The companion star to Antares, designated Antares B, is itself a massive hot blue star roughly 10 times the mass of our Sun, with a surface temperature around 35,000 degrees Fahrenheit. It is nearly invisible to the naked eye, swamped in the glare of the much brighter primary. It has been glimpsed primarily during the brief moments when the Moon passes in front of Antares and provides a natural coronagraph blocking the brighter star's light. From these challenging observations, astronomers have established that Antares B orbits the primary at a separation comparable to the distance between our Sun and the Oort cloud, completing one orbit in something over 1,000 years. During that orbit, it sweeps through regions of space filled with the material Antares A has been continuously shedding, creating complex structures in the circumstellar medium detectable at radio wavelengths. The two-star system is surrounded by an extended nebula of ejected material that serves as a fossil record of the mass loss history of Antares A over the past several 100,000 years. Measuring the true size of a star that appears as nothing more than a point of light, even through the most powerful telescopes, is not an obvious problem with an obvious solution. The physics required to solve it took 2 centuries to develop. The foundation is distance, established through parallax, the apparent shift of a nearby star against distant background stars as Earth moves around the Sun, shifting our observing position by 186 million miles over 6 months. From apparent shift and basic geometry comes distance. From distance plus measured apparent brightness comes intrinsic luminosity. From luminosity plus temperature, revealed by the spectrum of the star's light, which encodes surface heat in the wavelength of peak emission, comes radius, through the Stefan Boltzmann relation connecting energy output, temperature, and surface area. The cool surface of a red supergiant radiates less energy per square unit than a hot blue surface, so for equivalent total luminosity, it must be vastly larger. That is what the mathematics reveals. The measurement of stellar sizes is complicated by the fact that the largest stars resist clean edges. A red hypergiant does not end at a definite surface. Its atmosphere grades continuously from dense and hot near the center to thin and cool at the outer edges, and those outer edges are not stable. The star expands, contracts, ejects material, and behaves differently at different wavelengths. Measuring the diameter means specifying which layer you are measuring, which wavelength, and what point in the pulsation cycle the star was at when you observed. This is why the size figures for the largest known stars come with wide error bars, and why the rankings shift regularly as new data arrives. A star that holds the record 1 year may be revised downward the next when somebody rechecks the methodology with improved instruments or models. The fact that we can read the chemical composition of distant stars from their light across hundreds of light years is itself remarkable. When Isaac Newton first split sunlight into a spectrum in the 1660s, he saw a continuous rainbow. Careful examination in the early 19th century revealed dark lines crossing the spectrum at specific wavelengths. Absorption features produced by atoms in the outer atmosphere of the Sun. Each element absorbs light at specific wavelengths determined by quantum mechanics. By identifying which lines appear in a star's spectrum, astronomers can determine which elements are present, at what temperatures, and at what densities. This technique, spectroscopy, is how essentially everything we know about stellar composition has been established. In the constellation Cepheus, high in the northern sky, a star whose colour so captivated William Herschel in the 18th century that he nicknamed it the Garnet Star. Through even a modest telescope, it appears a deep, saturated ruby, a single drop of dark wine suspended against absolute black. Its formal designation is Mu Cephei. The light arriving tonight left the star around the time ancient Greek philosophers were laying the intellectual foundations of Western thought. The star measures roughly 1,400 times wider than our Sun, a diameter sufficient to swallow everything in our solar system out to the orbit of Saturn, Earth, Mars, Jupiter, the entire asteroid belt between them. All of it would be inside the star. Mu Cephei is a semi-regular variable, expanding and contracting on irregular cycles of 2 to 12 years, its instability driven by competing processes deep inside where fusion output, convective flows, and opacity changes fight for dominance without ever fully settling. Its luminosity of roughly 350 zillion times that of our Sun is concentrated heavily in the infrared, invisible to human eyes. To our naked eye, it appears as a faint reddish point. To infrared telescopes, it is one of the most luminous objects in the local region of the galaxy. It is also slowly shedding itself. The continuous outflow of its outer atmosphere has built a glowing shroud extending for light years around the star, a visible record of the material it has been losing for millions of years. The pulsation behavior of Mu Cephei connects to a broader family of variable stars that have been invaluable tools in cosmological measurement. Henrietta Swan Leavitt discovered the period luminosity relationship in Cepheid variable stars in 1912, which became the foundation of the extragalactic distance scale that Edwin Hubble later used to establish that other galaxies exist and that the universe is expanding. Mu Cephei is not a classical Cepheid but a semi-regular variable with less precisely periodic pulsations. But the underlying physics is related. Instability in the stellar interior drives pulsations, and the period of those pulsations encodes information about the star's physical state. One of the most physically bizarre stellar systems in the known catalogue sits in the same constellation as Mu Cephei. VV Cephei is a red hypergiant roughly 5,000 light-years away, with a diameter estimated between 1,000 and 1,600 solar radii. What makes it genuinely strange is not its size, but its gravitational arrangement. The system contains a second star, VV Cephei V, a substantial blue giant roughly 10 times wider than our Sun. VV Cephei A is so absurdly extended that the smallest star's orbital path takes it directly through the giant's outer atmospheric layers during part of every 20-year orbit. Every 2 decades, the blue companion plunges into the loosely held envelope and emerges months later, having carved through stellar atmosphere the way a finger drags through water. When this happens, the companion strips large quantities of material away, generates shockwaves through the giant's body, and pulls vast streams of gas into asymmetric structures. The brightness shifts take months or years to return to baseline after each pass. The scientific value of VV Cephei A as a natural laboratory is extraordinary. This periodic intrusion serves as a natural probe of the giant's atmosphere. As the blue star's light passes through progressively denser layers of the envelope before disappearing behind the giant, each layer imprints its own spectral signature, allowing astronomers to map the temperature, density, and composition of the atmosphere from the outside in. Titanium oxide, vanadium oxide, water vapor, and other molecules have been detected at specific depths in VV Cephei A's outer atmosphere through this technique, a level of detail otherwise completely inaccessible from 5,000 light-years away. The 20-year orbital period means that the complete experiment repeats within an observing career, allowing multiple generations of data to be compared as instruments improve. Each new orbital cycle is observed with better tools than the previous one, progressively filling in the details of the giant's atmospheric structure. VV Cephei A's outer atmosphere is so tenuously held together that material from it would register as less dense than the best vacuum achievable in a laboratory on Earth. The concept of a stellar surface loses most of its meaning for objects at this scale. In Cygnus, buried behind interstellar dust and invisible to the naked eye, KY Cygni held the record as possibly the largest star ever measured, briefly. Early estimates placed it at approximately 2,850 solar radii, a number that violated theoretical limits for how large a normal star can grow before Radiation pressure blows the outer layers away faster than gravity can retain them. The ceiling sits around 1,500 to 2 Ciron solar radii for even the most extreme red hypergiants. A star at 2,850 solar radii should not exist in a stable form. The appropriate scientific response was not to accept the measurement uncritically, but to go back and examine every assumption in the calculation. What the re-examination revealed was primarily a dust problem. The space between Earth and KY Cygni is filled with material that absorbs and scatters starlight in wavelength-dependent ways. If this interstellar extinction is not fully accounted for, a star appears dimmer than it actually is. A dimmer apparent brightness leads to an overestimate of the star's distance, which then produces an inflated calculation of its intrinsic luminosity, which produces an inflated size estimate. When astronomers rebuilt the calculation with improved dust extinction models and refined distance measurements, the figure fell substantially. Current estimates place KY Cygni between 1,030 and 1,400 solar radii, still one of the largest objects in the catalogue, no longer paradoxically large. The story illustrates something fundamental about how the leaderboard of cosmic extremes actually works. It is not a fixed list of confirmed facts. It is an ongoing refinement process where each generation of instruments produces better estimates, sometimes requiring significant revision. What looks like a champion one year may be revised the next when somebody rechecks the methodology. This is the science working as intended. Farther into Cepheus, V354 Cephei sits roughly 9,000 light-years from Earth, with estimates ranging between 600 and 890 solar radii. What makes it notable is where it sits, in the galactic suburbs, far from the dense star-forming regions near the center where massive stars typically form. The outer fringes of a galaxy are thin, cold, and quiet. Yet here is a star that by any reasonable measurement qualifies as a genuine hypergiant, sitting out in the stellar suburbs, far from where it should have been born. Either it formed from an unusual, local gas concentration that has since dispersed, or it was born elsewhere and drifted outward over millions of years. Either way, it breaks the usual rules about where objects this large are supposed to appear. Like other red hypergiants, V354 Cephei pulses, shedding material on each expansion phase that builds a glowing circumstellar shroud extending for light years around it. The carbon and oxygen being forged in its core right now might one day end up in the bones of creatures on a planet that does not yet exist, orbiting a star that has not yet been born. About 12,000 light-years away in the direction of Ara, Westerland 1 is one of the most violent stellar environments in the Milky Way. More than 200 massive stars crammed into a region only a few light-years across, all born within a few million years of each other. The dominant object, Westerland 126, carries size estimates between 2,000 and 2,500 solar radii, placing it at the absolute upper end of any confirmed measurement. At maximum, its outer edge extends past Saturn and approaches Uranus. It sits close to the Eddington limit, the theoretical ceiling where radiation pressure from the core equals gravity at the outer layers, and above which matter is expelled faster than gravity can hold it. How Westerland 1-26 holds itself together near or at that boundary is an active area of research. Some models invoke strong magnetic fields wrapped around the star that help confine the outer material. Others suggest the star is in genuine slow-motion disintegration, losing mass at a rate just below the catastrophic threshold. The Eddington limit deserves careful attention because it is the physical wall against which all the largest stars in this catalogue are pressing. Every photon produced by nuclear fusion in a star's core carries momentum. When a photon collides with an atom and is absorbed or scattered, some of that momentum is transferred to the atom, pushing it outward. For any given stellar luminosity, there is a corresponding amount of radiation pressure being exerted on the outer layers. For any given stellar mass, there is a corresponding gravitational pull drawing those layers inward. The Eddington limit is the luminosity at which these two forces exactly balance. For ordinary stellar chemistry, this limit corresponds to a maximum mass of roughly 150 solar masses. The most spectacular ongoing example of a star battling this limit is Eta Carinae, whose 1843 Run expelled 10 to 40 solar masses of material in a decade while releasing energy at rates comparable to a supernova, without actually destroying the star. That eruption created the twin-lobed homunculus nebula still expanding around the system today and remains one of the most studied objects in the southern sky. Westerland 1-26, hugging the Eddington boundary from the size direction rather than the mass direction, represents the same fundamental physics expressed at a different evolutionary stage. The cluster also harbors a magnetar, a neutron star with a magnetic field 1 trillion times stronger than Earth's, whose existence tells astronomers that the cluster's most massive stars were shedding material aggressively before they died. Standard stellar physics suggests that very massive stars should collapse directly to black holes rather than producing neutron stars. For a neutron star to form here, the progenitor must have lost enough outer mass first, almost certainly through violent episodic ejection similar to what Eta Carinae demonstrates. Inside the cluster, dozens of stars bright enough to individually cast shadows by night maintain a permanent pale, red twilight across any hypothetical sky within it. There would be no true darkness, no night as we know it, only the continuous combined light of monstrous companions ranging across the sky in every direction. Over a few 100,000 years, an observer inside Westerland 1 would watch multiple stars go supernova, each event temporarily adding a new source brighter than the full moon to an already luminous sky. Our solar system has lived its entire existence in a relatively quiet galactic suburb. The violent dynamism of clusters like Westerland 1 is the rule elsewhere, not the exception. Now we leave our own galaxy. The Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at 160,000 light-years, visible on dark southern nights as a faint smudge near the horizon. Inside it sits WOH-G64, a red hypergiant with a diameter estimated at 1,540 solar radii, its outer atmosphere extending past Saturn. The star is enclosed inside a thick torus of gas and dust it has been building for hundreds of thousands of years by shedding its own outer atmosphere. The torus is so dense that it absorbs most of the star's visible light. Observing WOH-G64 at optical wavelengths is like trying to see a candle through a wool blanket. The torus extends roughly 120 trillion miles around the star and contains several solar masses of accumulated material. OH-G64 sheds an amount of material equivalent to the full mass of our Sun every 10 zeros and years, a rate that challenges existing models of stellar mass loss. The energy driving this mass loss comes from the star's own luminosity acting on dust grains that condense in its cool outer atmosphere. Radiation pressure launches each grain outward and drags along the surrounding gas. But the rate at which this occurs in WOH-G64 exceeds what standard models predict for a star of its type. The star appears to be operating outside the standard parameter space, and the reasons remain incompletely understood. WOH-G64 is essentially eating itself from the outside in. When it finally explodes, the supernova shockwave will plow into the surrounding dust torus from the inside, lighting it up dramatically and creating one of the most spectacular supernova remnants the Large Magellanic Cloud has ever produced. Back in Cepheus, RW Cephei is a yellow hypergiant about 3,500 light-years away with size estimates ranging from 900 to 600 solar radii, not because of measurement imprecision, but because the star physically occupies different sizes at different times, swelling and shrinking in ways that shift its classification between stellar categories from year to year. High-resolution imaging has revealed it is not even approximately spherical. Visible asymmetries driven by enormous convection cells pushing material outward in some regions, while cooler gas sinks back in others, give it the appearance of a glowing, lumpy form rather than a smooth sphere. In 2022 and 2023, RW Cephei underwent a significant dimming similar to what Betelgeuse experienced in 2019, caused by a major ejection of dust-forming material that briefly blocked a substantial fraction of the outgoing light. Stars in the late stages of their lives eject increasingly large amounts of material in increasingly sudden events, each one peeling back another layer of the outer envelope. This is a pattern across the class. In Cygnus, NML Cygni sits behind dust thick enough to make it effectively invisible at optical wavelengths while blazing in the infrared, with estimates between 1,100 and 600 solar radii and mass loss rates delivering roughly 1 Earth mass every few months. In Sagittarius, VX Sagittarii measures around 1,520 solar radii and is shedding material containing the chemical products of its interior fusion: carbon, oxygen, neon, silicon, distributing them into the surrounding interstellar medium where they will eventually become part of the next generation of stars and planets. The material ejected by these hypergiants over their lifetimes is not simply lost. It moves slowly, a few miles per second, slow enough to pile up in thick circumstellar shells. When the star finally explodes, the supernova shockwave moving at thousands of miles per second slams into this slow-moving material. The collision lights up the shell from within, producing X-ray and radio emission that can persist for decades or centuries. The red hypergiants pre-manufacture the structures that will glow most spectacularly when they finally die. Every massive star's death is a delivery to the future. For decades, any conversation about the largest known star returned to Canis Majoris. Located roughly 3,900 light-years from Earth, it held estimates approaching 2,000 solar radii and occupied the top of every textbook list for years. Then the measurements were revised with better dust models and distance data, and the figure fell to somewhere between 1,300 and 1,700 solar radii. Still extraordinary, no longer the record holder. Revision is the story, provisional rankings perpetually updated, every champion eventually displaced by better data. Even at the low end of the revised figure, Canis Majoris would engulf everything inside Jupiter's orbit. The Hubble Space Telescope captured images of the chaotic, turbulent nebula of ejected material surrounding it, long arcs and dense knots and streaming filaments that look like an explosion frozen in time. Therefore not frozen. They are expanding at thousands of miles per second, the star still throwing material outward in irregular bursts, still building the cocoon that will eventually hide it from our view. The current confirmed record holder sits 20 Sierra light-years away in the direction of Scutum, Stephenson 218. Named from the catalogue of the cluster it inhabits, Stephenson 2, a collection of roughly 24 red supergiants apparently born together in a single massive star formation event about 20 million years ago. Most of the cluster's original most massive members have already burned through their lives and exploded. Stephenson 218 is among the survivors, and by far the largest. Current estimates place it at approximately 2,150 solar radii. Placing it at the center of our solar system puts its surface beyond Saturn. Jupiter is inside. The star radiates at roughly 440, times the luminosity of our Sun, almost entirely in infrared. Its surface temperature sits around 6,300 degrees Fahrenheit, cool for a star, which is why it glows the deep red visible in infrared imaging. The volume of Stephenson 218 requires unusual arithmetic to appreciate. Volume scales as the cube of the radius. Increasing the radius by a factor of 2,150 increases the volume by a factor of roughly 10 billion. The interior of Stephenson 218 could contain approximately 10 billion copies of our Sun, 10 billion suns inside a single star. The human population of Earth is around 8 billion people. There are more copies of our Sun inside Stephenson 218 than there are people currently alive on this planet. Light travelling at 186,000 miles per second needs approximately 9 hours to cross from one side to the other. The same journey across our Sun takes about 2 seconds. The scale becomes stranger when you consider density. Stephenson 218 does not contain 10 billion solar masses. Its total mass is estimated at only 20 to 40 times that of our Sun. The volume is 10 billion times larger. The mass is only 20 to 40 times larger, because the outer layers are almost incomprehensibly diffuse. Material from the outer atmosphere would be less dense than the air at the summit of Mount Everest, less dense than many laboratory vacuums on Earth. The star is a vast, nearly transparent fog of hydrogen atoms loosely held near a core that actually does the work. The surface gravity of a red hypergiant is one of the most strikingly low values in all of astrophysics for a star-scale object. surface gravity scales as mass divided by radius squared. For Stephenson 2-218, with its combination of relatively modest mass and enormous radius, the surface gravity works out to a tiny fraction of the surface gravity of our Sun. Material at the outermost detectable radius of the star is essentially at the escape velocity threshold, meaning that any small perturbation, a pulse from deep in the interior, a shockwave from a convection cell reaching the surface, a burst of radiation pressure, can accelerate that material past the escape velocity and launch it permanently into space. The red hypergiants are not just large, they are barely coherent. Stephenson 2-18 exists at the edge of what physics permits for a normal star. The theoretical ceiling, the Eddington limit, defines the point at which radiation pressure from the core exactly counterbalances gravity at the outer layers. Above that balance point, the outer material cannot stay attached and gets expelled. For stars with the chemical composition typical of the modern universe, this limit caps maximum masses at roughly 150 solar masses. Stephenson 2-18, with 20 to 40 solar masses spread across 2,150 solar radii, represents essentially the largest physical structure that normal stellar physics permits under current conditions. It sits at the wall. The relationship between stellar mass and lifespan follows a steep mathematical curve. Luminosity scales approximately as mass raised to the fourth power. A star 10 times more massive than our Sun is roughly 10,000 times more luminous. Its fuel consumption rate is 10,000 times higher. Its hydrogen supply is only 10 times larger. The resulting lifespan is roughly 1,000 times shorter. The most massive stars in this catalogue have main sequence lifetimes of only a few million years. In that time, they progress through the entire arc of stellar evolution that will take our Sun 10 billion years to partially complete. The Hertzsprung-Russell diagram, the fundamental organizational chart of stellar astronomy, plotting luminosity against surface temperature, makes this visible instantly. The red giants and hypergiants occupy a separate region in the upper right, where luminosities are high and temperatures are low. Getting to that region requires leaving the main sequence, which happens when the core hydrogen supply is exhausted. Every red hypergiant you see is a star in its final chapters. The color tells you the chapter number. What happens inside a star's core when it starts fusing heavier elements beyond hydrogen is one of the most dramatic acceleration stories in physics. The helium burning phase lasts roughly 10 to 20% as long as the hydrogen phase. Carbon burning compresses into perhaps a few hundred years. Neon burning takes perhaps a year. Oxygen burning perhaps 6 months. Silicon burning, the final stage before iron ends the sequence, takes only a few days. Each new fuel releases less energy per reaction than the previous one. The core is running toward a wall at exponentially increasing speed, burning through millions of years of prior history in days at the end. The star's entire outer structure, unchanged for millions of years in its broad red supergiant shape, is ignorant of this acceleration happening at the center. The surface of Stephenson 2-18 today looks essentially the same as it did a million years ago. But the core is somewhere completely different, racing toward a collapse that may now be measured in centuries. The collapse of a hypergiant's iron core proceeds through stages that compress matter to conditions existing nowhere else in the observable universe. When the iron core's mass exceeds the Chandrasekhar limit, roughly 1/4 solar masses, electron degeneracy pressure fails and collapse begins. Within less than a second, the inner core reaches nuclear density, roughly 100 trillion times the density of water. The strong nuclear force becomes repulsive and the collapse rebounds. The inner core bounces and sends a shockwave outward through the still collapsing outer layers. When the shockwave finally breaks through the star's surface, the explosion begins. The neutrinos produced in the collapsing core carry away more than 99% of the total energy released, moving through the collapsing star and outward into space at nearly the speed of light. A Milky Way supernova's neutrino burst would arrive at Earth tens of seconds before the optical explosion became visible, which is why neutrino detectors are watched carefully as potential early warning instruments for nearby stellar deaths. A supernova releases energy equal to the total light output our Sun will produce across its entire 10 billion year lifetime, delivered in seconds. For a brief period, typically a few weeks, it outshines the entire galaxy containing it. A single dying star produces more light than billions of normal stars combined. Inside the explosion, temperatures reach billions of degrees, and pressures exceed anything in the normal stellar environment. These extreme conditions allow atomic nuclei to fuse in sequences that cannot occur in a stable stellar core. Gold, platinum, uranium, and many other heavy elements are synthesized in supernova explosions and distributed into the surrounding gas by the expanding shockwave. Every gold atom in any object on Earth was forged in a stellar explosion and spent billions of years in the interstellar medium before being swept into the cloud that became the solar system. Neutron star mergers, confirmed by gravitational wave detection in 2017, produce additional heavy elements through rapid neutron capture. The first detected merger appears to have synthesized an amount of gold and platinum comparable to several times the mass of Earth in a single event lasting fractions of a second. Every ring, every coin, every piece of gold jewelry contains atoms created in a collision between two neutron stars, themselves the remnants of massive stars that lived and died billions of years ago. After a supernova, the collapsed core becomes either a neutron star, 12 miles across, containing more mass than our Sun, spinning rapidly, generating beams of radio waves detectable as pulsars, or for the most massive cores, a black hole where gravity becomes so extreme that not even light can escape. For the most extreme massive stars, pair instability supernovae can occur where core temperatures become high enough for photons to spontaneously convert into electron-positron pairs, removing radiation pressure, triggering catastrophic collapse and explosive fusion so complete that the entire star is obliterated. No remnant. The object ceases to exist as a coherent physical structure, replaced only by an expanding cloud of debris. These events were more common in the early universe, when massive population 3 stars regularly exceeded the required mass threshold. For the most massive and rapidly rotating stellar cores, twin jets of relativistic material fire outward along the poles at close to the speed of light, a hypernova with an associated gamma-ray burst, detectable from galaxies more than 10 billion light-years away. If such a jet were aimed at an inhabited planet within a few hundred light-years, the arriving radiation would strip the ozone layer and sterilize the surface. Supernova remnants preserve information about the explosion that created them across timescales of tens of thousands of years. The expanding shell carries the chemical composition of the progenitor star's layers, frozen at the moment of the explosion and spread across a growing volume of space. The Cassiopeia, a remnant about 350 years old as seen from Earth, has been studied in X-rays, radio waves, visible light, and infrared in extraordinary detail. Images reveal knots of iron and silicon and argon ejected asymmetrically by the explosion, providing direct evidence of the three-dimensional structure of the dying star's core at the moment of collapse. These elemental knots are moving at several thousand miles per second and will continue expanding for thousands of years. They are material forged in the last seconds of a massive star's life, still moving through space, still carrying the chemical record of what that star contained. The Crab Nebula, the Veil Nebula, the Cygnus Loop. All of them are the lingering aftermath of stars that ended violently long ago, each one telling the story of a hypergiant or supergiant that completed its life cycle in a brilliant flash and is now leaving its mark on the galaxy. The connection between stellar rotation and the violence of a star's death is counterintuitive. A slowly rotating core collapses more or less symmetrically, producing a standard supernova. A rapidly rotating core develops a centrifugal bulge as it collapses, flattening into a disk configuration and leaving the polar regions comparatively clear, into which material channeled along the rotation axis can be ejected as twin jets at close to the speed of light. The same progenitor star, with the same mass and the same core composition, produces dramatically different outcomes depending on whether it retained its angular momentum or lost it. Binary stellar interactions add further complexity. Mass transfer between stars changes the rotation rates, masses, and internal compositions of both members, producing evolutionary paths that single-star models cannot predict. The binary fraction among massive stars is remarkably high. Modern surveys suggest that more than half of all O-type and B-type stars have at least one gravitationally bound companion. Some of the most unusual observed supernovae in external galaxies show properties best explained by a progenitor that was in a tight binary and had already transferred significant mass to a companion before exploding. The early universe had no heavy elements. The first stars, population 3, formed from gas that was almost perfectly pure hydrogen and helium. Without heavier elements to efficiently radiate heat during collapse, the gas stayed warmer longer and had to reach higher masses before fusion could ignite. These first stars are estimated to have ranged from roughly 100 to 1,000 solar masses, burning at surface temperatures exceeding 50 degrees Fahrenheit, pumping ultraviolet radiation into the surrounding gas at rates sufficient to ionize hydrogen across enormous distances. This process, cosmic reionization, transformed the universe from a dark, murky place where light could barely travel before being absorbed into the transparent cosmos where we can now observe galaxies billions of light years away. Every observation we make of anything beyond our immediate neighborhood is possible because these first stars made it so. The formation of population 3 stars involved physical conditions so different from modern star formation that the process produced a completely different population of objects. In the modern universe, star-forming molecular clouds are permeated with dust grains and complex molecules that make them efficient radiators. When a portion of such a cloud begins to collapse under gravity, the kinetic energy of the infalling material heats the gas, but this heat is radiated away efficiently, allowing the collapse to continue and the cloud to fragment into many pieces, each one collapsing to form a star of modest mass. In the early universe, no dust existed and no complex molecules existed. The only coolant available was molecular hydrogen, far less efficient at radiating away heat. The collapsing gas stayed warmer longer and could not fragment into small pieces. Instead, material continued to fall onto a single protostellar object, growing its mass far beyond what modern star formation permits. The minimum mass for a population 3 star may have been around 10 solar masses, with typical masses of a few hundred and a maximum that theoretical models place at several thousand. The deaths of population 3 stars seeded the universe with the first heavy elements, carbon, oxygen, silicon, iron, that all subsequent stellar generations have inherited. Their supernovae scattered these elements into the surrounding gas clouds. The next generation of stars formed from this enriched material. The generation after that was richer still. Each cycle of massive stellar birth and death added to the chemical inventory available for subsequent generations. The chemical legacy of population 3 stars is preserved in metal-poor stars in the Milky Way's outer halo, their element ratios matchable against specific explosion models. Archaeological astronomy, reading the record of events that happened more than 13 billion years ago from the composition of stars still burning today. Different explosion mechanisms produce different ratios of elements. A pair instability supernova produces a different chemical fingerprint than standard core collapse. By fitting the observed element ratios in the oldest metal-poor stars to theoretical explosion models, researchers can constrain the masses, rotation rates, and explosion mechanisms of population 3 stars that no one has ever directly observed. The metallicity of a star, the proportion of elements heavier than helium it contains, profoundly affects how much mass it loses through stellar winds during its lifetime. Heavier elements are more efficient at absorbing radiation, so a metal-rich star experiences stronger radiation pressure on its outer layers and loses mass more readily than a metal-poor star of the same mass. In the very early universe, population 3 stars were metal-free, meaning their mass loss rates were far lower than those of equivalent stars today. They could retain more of their original mass through their lives, reach higher maximum masses at the end of the main sequence, and potentially produce pair instability supernovae at rates far higher than anything seen in the metal-enriched modern universe. As successive generations of massive stars lived and died, the metallicity of the interstellar medium increased, and the mass loss rates of subsequent massive stars increased with it. The giant stars in this catalogue are less extreme than their ancient ancestors, precisely because they are enriched. Their inherited chemistry now drives continuous mass loss that gradually erodes their outer envelopes. Throughout their lives, the early universe may also have hosted quasi-stars, objects powered not by nuclear fusion but by black holes at their centers feeding on surrounding gas. The radiation from a feeding black hole would support an enormous outer envelope against gravity. Theoretical models predict quasi-star sizes of 50,000 to 100,000 solar radii, diameters of roughly 430 billion miles, approximately 48 times the diameter of our solar system. The interior of such an object would contain hundreds of thousands of solar systems worth of volume. When the central black hole grew large enough that its radiation pressure dispersed the outer envelope, what remained would be a massive black hole seed that could continue growing through conventional accretion over billions of years, possibly explaining how supermassive black holes reached billions of solar masses when the universe was less than 1 billion years old. The lifespan of a quasi-star, estimated at roughly 7 million years, is several times longer than the lifespan of the most massive normal stars. The reason is the energy source. A black hole feeding on surrounding material is extraordinarily efficient, allowing the quasi-star's central black hole to support an enormous outer envelope for millions of years while steadily growing. James Webb Space Telescope observations have already detected active galactic nuclei less than 500 million years after the Big Bang, with implied black hole masses that challenge simple growth models. Quasi-stars may be a necessary part of the explanation. Dark stars push theoretical extremes further. If dark matter consists of particles capable of annihilating each other and releasing energy, those annihilation events could heat a collapsing gas cloud from within, preventing it from reaching the densities needed for nuclear fusion and, instead, producing an enormous, diffuse, slowly radiating structure. Some theoretical models place dark star sizes in the range of millions of solar radii, objects whose diameters would exceed the typical spacing between stars in the present-day galaxy. At those scales, the concept of a stellar surface loses all meaning. The object would not end but simply become increasingly thin and cool as you moved outward, eventually grading into something indistinguishable from an extremely dense interstellar cloud. Whether dark stars ever existed depends entirely on the nature of dark matter, which remains one of the most pressing open questions in physics. The ongoing mystery of what exactly dark matter is has direct implications for whether dark stars ever existed. If dark matter consists of weakly interacting massive particles capable of self-annihilation, then in the very early universe, when dark matter was orders of magnitude denser than it is today, annihilation rates could have been high enough to power stellar-scale objects for millions of years. The answer would resolve whether the largest objects in the history of the universe were even larger than quasi-stars. The process of star formation is connected to the deaths of previous generations. The molecular cloud from which our solar system formed was assembled from material enriched by many cycles of stellar birth and death. The isotopic composition of certain elements in ancient meteorites provides direct evidence. Short-lived radioactive isotopes whose half-lives are far too short to have survived from the Big Bang are found in meteorite inclusions at abundances indicating they were injected by a nearby supernova within a few million years of the solar system's formation. The specific isotopes found, including aluminum-26 and iron-60, are produced in specific kinds of stellar explosions, and their presence in solar system material is a direct chemical fingerprint of a massive star that died in our cosmic neighborhood just before or just as our sun was forming. We have evidence in the rocks of our solar system that a massive star died nearby, and that its death contributed to the formation of everything we are part of. The cumulative effect of billions of years of stellar nucleosynthesis and distribution on the chemical composition of the universe is one of the most remarkable stories in all of physical science. When the universe was 3 minutes old, it contained hydrogen, helium, and trace amounts of lithium. Every heavier element has been manufactured since then, inside stars and distributed by stellar deaths. The specific carbon atoms in your body were once inside a stellar core, fused there from helium at temperatures of several 100 million degrees, under pressures that exceed anything achievable on Earth's surface. They were blasted out in an explosion that briefly outshone the entire galaxy. They spent millions of years in the interstellar medium, drifting as part of a diffused gas cloud at temperatures only a few degrees above absolute zero. They were swept into a collapsing molecular cloud as gravity pulled the cloud inward. They became part of a protostellar disk circling a newly forming sun. They were incorporated into a rocky planetesimal. They became part of the planet you stand on. They were incorporated into the chemistry of life. They became part of you. At every step, the physical process that moved them to the next stage was traceable to the deaths of massive stars. The largest stars in this catalogue are not decoration at the extreme edge of a scale chart. They are the most productive nodes in the manufacturing and distribution system that created the conditions for everything you are made of to exist anywhere in the universe. The implications of the light delay extend beyond the haunting possibility that some of the stars we observe have already exploded. In the framework of special relativity, the concept of simultaneous events becomes meaningless for observers separated by large distances. What we observe when point a telescope at Betelgeuse is not the star as it is, but as it was. The difference is not merely a delayed snapshot of an ongoing reality, as if we had a slow news feed. It is the only reality accessible to us because no information can travel faster than light, and therefore no description of the star's present state can ever reach us without the delay. The universe enforces a kind of epistemic humility on astronomy. We can describe the past with great precision and the future with statistical confidence, but the present state of distant objects is forever inaccessible. For stars like Betelgeuse and Antares that are in unstable late-life phases and could explode on astronomical timescales of tens of thousands of years, this means we are genuinely uncertain whether the objects we are observing still exist in the form we see them. On some future night, for some of these objects, a new bright point will simply appear in the sky where no star was visible the night before. It will be the light from an explosion that happened long ago, finally completing its journey. The last great supernova visible to the naked eye was recorded in 1054, when Chinese astronomers noticed a new star in Taurus bright enough to be seen during daylight for weeks. The remnant of that explosion is now the Crab Nebula, one of the most studied objects in astrophysics. If Betelgeuse detonates tomorrow, the light will arrive at Earth in the year 2666, long after anyone living today has been gone. If Antares explodes tonight, the signal will arrive in roughly 550 years. We cannot know what is happening to these stars right now. We can only wait for whatever light they are currently sending to complete its journey. The discovery of gravitational waves beginning in 2015 opened an entirely new channel for observing the aftermath of massive stellar deaths. Binary black hole mergers, detected as chirps of gravitational radiation, provide direct mass measurements of stellar remnant black holes. The distribution of these masses across the detected population is a map of the mass loss histories of massive stars across the universe, integrated over cosmic time and metallicity distribution. Each detected merger is a message from two massive stars that lived and died. The search for more extreme stars continues with each new generation of instruments. The Milky Way contains hundreds of billions of stars. The fraction surveyed in sufficient detail to identify extreme objects is small. The regions most likely to harbour the largest stars, dense clusters near the galactic centre, regions embedded in thick dust columns, are precisely the hardest to study. The James Webb Space Telescope with its infrared capabilities, the Gaia mission's billion-star parallax catalogue, the extremely large telescope under construction in Chile with its 39-metre primary mirror, each extends the census further into previously inaccessible territory. The galactic centre region alone, within a few thousand light-years of the supermassive black hole at the Milky Way's core, contains multiple massive star-forming clusters discovered only in the infrared era. Some of these clusters contain stars as extreme as anything in the wider known catalogue. but they were entirely unknown to astronomy before infrared surveys began penetrating the obscuring dust. The true distribution of extreme stars in the Milky Way is almost certainly more extensive than the confirmed catalogue suggests. Every new survey, every new infrared image that penetrates a previously opaque dust column, is an extension of the same project that has been running since the 19th century. The project of finding out what is actually out there. The role of massive stars in regulating star formation across entire galaxies is one of the most important processes in galaxy evolution. Massive stars are not passive inhabitants of their environment. They actively reshape the gas and dust around them from the moment they form. The intense ultraviolet radiation from hot young massive stars ionizes the surrounding hydrogen gas, creating glowing regions visible across galactic distances. The stellar winds from these same stars push material outward, creating cavities in the surrounding interstellar medium. When the stars eventually explode, their supernova shockwaves sweep up and compress nearby gas clouds, potentially triggering new rounds of star formation in the compressed shells, while simultaneously dispersing other gas clouds that were in the process of collapsing. Without this feedback, theoretical models predict that galaxies would convert their available gas into stars far more quickly than is actually observed. The massive stars that form first act as a regulatory mechanism for all subsequent star formation, controlling the pace at which the raw material of galaxies is processed into stellar populations. The compact remnants left behind by the deaths of massive stars are not static endpoints. A neutron star formed in a supernova may spend billions of years as a pulsar, gradually spinning down and losing rotational energy as electromagnetic radiation. Eventually, its spin rate decreases to the point where the pulsar beam falls below detectable threshold, and the neutron star becomes invisible in radio wavelengths. It continues to cool over billions of years, eventually becoming a cold, dark object that emits no detectable radiation. There may be a vast population of such cold, dark neutron stars distributed throughout the galaxy from all the massive stellar deaths over the past 13 billion years. A stellar mass black hole formed in the collapse of a hypergiant's core drifts through the galaxy in the same way, occasionally accreting a brief stream of gas from a cloud it passes through and producing a fleeting X-ray flare that reveals its position. The descendants of the stars in this catalogue are everywhere in the galaxy, in forms we mostly cannot see: cold neutron stars, isolated black holes, slowly cooling white dwarfs. The visible stars are a small fraction of all the stellar material that has ever existed. Most of it has already gone dark. The stars we have visited tonight are not curiosities. They are the mechanism by which the universe manufactures the raw materials of complexity. In the young universe, almost all matter was hydrogen and helium. Every element heavier, every atom that forms a rock or a molecule or a living cell had to be built inside stars and distributed by their deaths. The carbon in your cells was assembled in a stellar core, the oxygen in the atmosphere, the silicon in rocks, the iron threading through every living cell, the gold and platinum and uranium, all manufactured through the fusion processes. We have been following through this catalogue, scattered into the interstellar medium by explosions and stellar winds across billions of years and multiple generations. We are not poetically made of stardust. We are precisely and specifically assembled from material that was processed inside stars and delivered here by their deaths. The chain of custody is traceable, the physics is understood, the history is written in the isotope ratios of ancient meteorites and the chemical abundances of the oldest stars in the galaxy. Looking at the night sky after everything in this catalogue, the experience of it changes. The familiar patterns overhead are not background decoration. They are active objects in the middle of physical processes that built everything around you. The red stars visible on a winter or summer night are at various points in the manufacturing process. Some are currently making the carbon, some are in the process of distributing it. Some already have, and what you see is the light from their long cooling remnants. The supply chain that produced every complex atom in the visible universe runs through objects like the ones in this catalogue, and the sky is the record of that supply chain operating in real time across distances that make the whole arrangement difficult to hold in mind at once. The question of what it means to say that a star is the largest ever to have existed depends on when in cosmic history you are asking. In the first few 100 million years after the Big Bang, the largest objects were the population 3 stars, and the hypothetical quasi-stars and dark stars, which may have reached sizes orders of magnitude beyond anything in the current universe. The current largest known star, Stephenson 218 at roughly 2,150 solar radii, represents the upper end achievable under present conditions. The era of red hypergiants like Stephenson 218 is not eternal. It is a specific phase in cosmic history when the conditions for forming extremely massive stars are present but declining. Every object in this catalogue will eventually be gone, not merely dead but dispersed, its material folded back into the galaxy, reformed into new structures. The universe does not preserve its monuments, it recycles them. Betelgeuse will become an expanding shell of debris persisting for tens of thousands of years before thinning and merging with the surrounding gas. The neutron star, or black hole at its center, will drift through space for billions of years. Stephenson 218 will explode or collapse and leave behind a compact remnant embedded in the dust of scutum. The material that currently constitutes these giants will eventually be incorporated into the next generation of stars and the generation after that. Some will form planets. Some of those planets will have conditions warm enough for liquid water and complex enough chemistry for biology. The atoms currently inside Stephenson 218 will not cease to exist when the star does. They will continue transformed in whatever the universe builds next from the wreckage of what came before. The universe does not create complexity and then preserve it. It creates complexity, uses it as raw material for the next cycle of creation, and keeps going. The largest stars are the most productive wrecking operations in that project. Everything we know, everything we are, everything this planet contains is downstream from this process, made possible by an unbroken chain of stellar birth and death stretching back 13 billion years to the first population 3 giants burning in the dark. The search for the largest star never really ends because the universe is too large and too opaque for any complete inventory. The current leaderboard will be revised, objects near the top will be measured more precisely and may be displaced. Objects not yet discovered will be found in dust-embedded clusters and added at positions that shift everything else down. The question of what the largest star ever to have existed was, may never be answerable at all, because the objects that might have held that title burned in the first few 100 million years of cosmic time and left behind only the indirect evidence of their chemistry and the black holes that survived them. But the pursuit of these questions has produced an understanding of stellar physics, nuclear synthesis, galactic chemical evolution, and the origins of the material that makes up everything visible in the universe. Every answer in this catalogue arrived through measurement, mathematics, and physical reasoning applied to light that crossed thousands of light years to reach a detector built by people on a planet whose existence is itself a consequence of stellar deaths. That is what the largest stars mean in the end. They are the reason there is anything worth looking at. The answers are always provisional, the questions are permanent, and the sky above you tonight holds more of both than any catalogue has yet captured. The Hertzsprung-Russell diagram, the fundamental organizational chart of stellar astronomy, plotting luminosity against surface temperature for every known star, reveals something immediately when you look at where red supergiants sit relative to the full population. The vast majority of stars cluster along a diagonal band called the main sequence, where stable hydrogen-burning objects of different masses arrange themselves from hot bright in the upper left to cool dim in the lower right. This is where our Sun sits. This is where Sirius sits. This is where the overwhelming majority of stars in the galaxy spend most of their existence. The red giants and hypergiants in this catalogue occupy a separate region in the upper right of the diagram where luminosities are high and temperatures are low. Getting to that region requires leaving the main sequence, which happens when the core hydrogen supply is exhausted. The most massive stars cross from main sequence to hypergiant status rapidly, spending only a small fraction of their total lives in the red phase before exploding. Betelgeuse, Antares, Mu Cephei, and all the red hypergiants sit in this upper right territory, and their presence there encodes their evolutionary state: old, expanded, cool, and approaching the end. The diversity of endpoints after a supernova depends on the mass of the collapsing core. A core between roughly 1, 4 and 3 solar masses becomes a neutron star, 12 miles across, containing more mass than our Sun, spinning rapidly, and generating beams of radio waves detectable as pulsars. Neutron stars are genuinely strange objects. They contain roughly 4 times the mass of our Sun packed into a sphere about the size of a city. A teaspoon of neutron star material would weigh billions of tons at Earth's surface. The density exceeds anything achievable through any process in normal stellar evolution. The nuclear matter inside a neutron star is so compressed that the individual protons and electrons that make up ordinary matter are merged into neutrons, and the entire object behaves like a single enormous atomic nucleus. For the most massive collapsing cores, not even neutron star structure can hold. The collapse continues past neutron density into a black hole, a region where space-time curvature becomes so extreme that not even light can escape from inside the event horizon. The black holes left behind by hypergiant deaths drift through the galaxy in darkness, occasionally revealing their presence when they accrete material from a passing gas cloud, or when a companion star feeds material into the black hole and generates X-rays. The night sky seen from inside a cluster like Westerland 1 would not just be bright, it would be dynamic in ways our sky never is on human timescales. Over the course of a few 100,000 years, an observer in that cluster would watch multiple stars go supernova, each event temporarily adding a new source brighter than the full moon to the already luminous sky. The shock waves from these explosions would ripple through the cluster, compressing gas clouds, stripping material from companion stars, and potentially triggering new rounds of star formation from compressed shells. The Earth's cluster would be evolving visibly on timescales of tens of thousands of years, adding new members as triggered star formation produced them and losing old members to supernova explosions. Our own solar system has lived its entire existence in a relatively quiet galactic suburb, insulated from most of this violence by distance and the low local density of massive stars. The occasional nearby supernova has likely affected Earth's history. Possible correlations between ancient mass extinctions and supernova events remain an area of active research, but nothing comparable to what a planet inside Westerland 1 would experience routinely. We exist in the calm. The chemical enrichment of the universe over cosmic time is not a smooth or uniform process. Different elements are produced at different rates by different types of stellar events, and the relative abundances of elements in any region of the galaxy reflect the specific history of star formation and stellar death in that region. The cores of elliptical galaxies, which stopped forming stars billions of years ago, have chemical compositions frozen at the state they reached when star formation ended. The disks of spiral galaxies like the Milky Way have been continuously enriched by successive generations of star formation and supernovae. The outer halos of galaxies preserve the chemical signatures of the very first generation of enrichment when population 3 stars spread the first heavy elements into previously pristine gas. By mapping the chemical composition of stars at different locations and at different ages, astronomers can reconstruct the full history of nucleosynthesis in a galaxy, which types of stars contributed which elements, in what proportions, and on what time scale. This is galactic archaeology, using the preserved chemical records in individual stars as documents in a history that extends back to the first stellar generations. The mass ejected by red hypergiants over their lifetimes actively contributes to the structure of the surrounding interstellar medium. Outflowing material from a red hypergiant moves relatively slowly, a few miles per second, slow enough that it piles up in a thick shell around the star rather than dispersing immediately. Over hundreds of thousands of years, this shell grows to enormous size, surrounding the star in a cocoon of previously ejected material. When the star finally explodes, the supernova shockwave moving at thousands of miles per second slams into this slow-moving circumstellar shell. The collision is highly supersonic. The resulting explosion lights up the shell from within, producing X-ray and radio emission that can persist for decades or centuries as the shockwave and shell interact. The chemical richness of the circumstellar material at the moment of this collision, carrying the products of the hypergiant's late-stage fusion, distributed in the complex layered shell structure the stellar wind has built, makes these interaction events some of the most chemically productive environments in the galaxy. The binary fraction among massive stars is remarkably high. Modern surveys suggest that more than half of all O-type and B-type stars have at least one gravitationally bound companion, and some clusters show close binary fractions approaching 100% for the most massive members. This prevalence has profound implications for stellar evolution, because binary interaction dramatically changes the evolutionary path of both stars in the system. The more massive star reaches the end of its main sequence first and begins expanding toward the red giant phase, while its companion is still in stable hydrogen burning. As the first star expands, its outer envelope can overflow a theoretical boundary called the Roche lobe and begin transferring material directly onto the companion. This mass transfer changes both stars profoundly. The donor star loses mass and evolves differently than it would in isolation. The recipient gains mass and may be pushed into a faster evolutionary track. In extreme cases, both stars temporarily share a single puffed-up common envelope, which is then ejected as both stars emerge more compactly bound. These processes can produce stars with masses and internal structures that simple single-star models cannot predict, which is one reason why the very largest stars we observe often have properties that resist simple explanation. The question of what happens when a star of Betelgeuse's mass finally collapses deserves a detailed answer, because the sequence of events between stable red supergiant and supernova remnant is one of the most violent processes in the universe, and it unfolds on a timescale measured in seconds. Everything that is about to be described, the iron core collapse, the neutron star bounce, the neutrino burst, the shockwave breaking through the stellar surface, happens within roughly 1 second for the core and within hours for the outer star. The star has been glowing steadily for millions of years. It has been building up the iron core that will end it for perhaps a few thousand years of silicon burning. In the final day of silicon burning, the iron core reaches the Chandrasekhar mass limit. Electron degeneracy pressure, the quantum mechanical resistance that has been supporting the core against gravity, can no longer hold. The core begins to collapse. In the next 250 milliseconds, the inner portion of the iron core compresses from about the size of Earth to about the size of a city. The density exceeds nuclear density. The strong nuclear force becomes repulsive. The inner core bounces, sending a shockwave outward. Simultaneously, the enormous flood of neutrinos produced in the collapsing core begins pouring through the rest of the star and into space. Some of this neutrino energy is deposited in the stalled shockwave. Reviving it, the shockwave pushes outward through the star's outer layers. Hours later, it breaks through the surface and the supernova begins. The star that spent millions of years building up to this moment dies in less time than it takes to eat a meal. The first direct image of a stellar surface other than the Sun changed how astronomers think about the largest stars as objects rather than as numbers. When Hubble resolved Betelgeuse's disk in 1996 and showed a bright spot on its surface, the star transformed from an abstract set of measurements into a place, a specific location in space with specific features that could be tracked. Since then, the images have improved to the point where individual convection cells can be followed across multiple observing seasons. Modern interferometric instruments have now resolved the disks of Antares, Mu Cephei, and several other red supergiants, showing each of them to have the same kind of active asymmetric surface that Betelgeuse pioneered in our understanding. These surfaces are not smooth. They are covered by large, irregular bright spots and darker regions. They breathe and pulse and eject material. They look like nothing in our everyday experience, but they look like something, like real places, with real physical processes unfolding across them in real time. The study of massive stellar populations in nearby galaxies accessible to detailed observation provides a way to test stellar evolution models against samples that differ in metallicity and star formation history from the Milky Way. The Magellanic Clouds have lower metallicity than the Milky Way, meaning their massive stars lose mass more slowly and can potentially reach larger final masses before exploding. This prediction is testable. If lower metallicity allows more massive final explosions, the Magellanic Clouds should show a higher rate of the most energetic supernova types than the Milky Way. Several observed supernovae in the Magellanic Clouds have indeed shown properties consistent with more massive progenitors than typical Milky Way events. The W8G64 hypergiant in the Large Magellanic Cloud may represent a direct example of a star that was able to grow to its extraordinary current size precisely because the lower metallicity of that galaxy allows it to retain more mass. As telescopes improve and supernova samples in nearby galaxies grow, these cross-environment comparisons will become increasingly powerful tests of the physics we use to model the most massive stars. The role of magnetic fields in the lives of the largest stars extends beyond their influence on stellar winds and rotation. Strong internal magnetic fields can also affect the mixing of nuclear process material between different layers of the stellar interior. In a non-magnetic star, mixing between the convective core and the surrounding radiative envelope is limited to regions where convection explicitly operates. Magnetic fields can drive additional mixing at these boundaries through magnetic buoyancy instabilities. The tendency of magnetically buoyant field structures to rise through surrounding material and carry chemically processed gas with them. This extra mixing can bring helium produced in the core into the outer layers and fresh hydrogen from the outer layers into the burning region, modifying the star's chemical composition in ways that affect its eventual size, luminosity, and explosion mechanism. For the most massive stars, where the consequences of small composition changes are amplified by the steep mass-luminosity relationship, magnetic mixing could shift a star's final outcome from one category to another. The difference between a star that produces a normal supernova and one that produces a pair instability event may, in some cases, come down to whether magnetic mixing kept fresh hydrogen available in the core a little longer. The full scale of stellar diversity extends from red hypergiants at the extreme upper end. Objects so large they would encompass the entire inner solar system down through ordinary giants, main sequence stars of various masses, low-mass red dwarfs barely large enough to sustain nuclear fusion, and finally to brown dwarfs, substellar objects that failed to reach fusion temperatures and simply glow dimly from their formation heat. The smallest confirmed brown dwarfs are only a few percent the radius of our Sun. The ratio between the smallest stellar-scale objects and the largest confirmed stars is roughly 40,000 to 1 in radius and roughly 60 trillion to 1 in volume. The universe produces self-luminous objects across an incomprehensible range of sizes within a single, physical category. Every object in that range operates through the same fundamental principle: gravity compressing matter until fusion or contraction generates enough energy to maintain equilibrium. But the manifestations of that principle range from the barely there glow of a failed star to the blinding enormity of a star that could swallow an entire planetary system. The catalogue of the largest known stars is, in a meaningful sense, a catalogue of endings. Every object on the list is in the late stages of its existence, expanded and swollen and shedding material, burning through its final fuel reserves on a timeline that ranges from tens of thousands to a few million years. None of them will look like this forever. Betelgeuse will explode, Antares will explode, Mu Cephei will explode, Stephenson 218 will explode or collapse. The red hypergiant phase is not a stable endpoint. It is a brief, dramatic interlude between the long productive main sequence life of a massive star and the violent endpoint that terminates every one of them. What makes this phase so scientifically rich is precisely its brevity. We are catching these stars in a narrow window of their existence, in the specific configuration that makes them simultaneously the largest known objects and among the most physically unstable. Studying them now, while they are accessible, while they are still glowing and pulsing and shedding material in detectable patterns, is an opportunity that will not recur once they explode. Each one is a temporary laboratory. Each observation is an opportunity to learn something that will not be available again. The night sky above you right now contains all of this. It contains Betelgeuse's 640-year-old shoulder, possibly the ghost of a star that already exploded. It contains Rigel's medieval light, Antares glowing its ancient blood-red signal across 550 light-years. Beyond what naked eyes can reach, it contains Mukeffe in the northern Cepheus, NML Cygni hidden behind its dust, Stevenson 218 broadcasting infrared from 20,000 light-years away in Scutum. It contains the chemical legacy of every star that ever died, distributed through the interstellar medium and waiting to be incorporated into the next round of stellar birth. It contains the compact remnants of every massive star that exploded in the history of the galaxy. Cold neutron stars, silent black holes, the slowly cooling embers of white dwarfs. The sky is not empty space decorated with distant lights. It is a functioning system, ancient and ongoing, that has been building chemical complexity for 13 billion years and is still at it. The largest stars in this catalogue are the most productive elements of that system. They always have been. The connection between the deaths of massive stars and the formation of new planetary systems represents one of the most direct causal chains in astrophysics. When a supernova shockwave hits a nearby molecular cloud, it does two things simultaneously. It compresses the cloud, lowering the threshold for gravitational collapse to begin, and it injects freshly synthesized heavy elements into the cloud's chemistry. The compressed regions of the cloud can collapse into new protostars on timescales much shorter than unperturbed molecular clouds require. These new protostars form surrounded by disks of enriched gas and dust that will eventually coalesce into planetary systems. The planets that form from these disks inherit the chemical composition of the cloud, which now includes the heavy elements distributed by nearby supernova. Rocky planets require silicon, magnesium, iron, and other elements heavier than hydrogen and helium. Every rocky planet in the galaxy owes the material that makes it rocky to a sequence of massive stellar deaths stretching back through cosmic time. Earth's specific rocky composition, the precise ratios of silicon to iron to magnesium that determine its density, its mantle structure, its core, reflects the particular history of supernovae that enriched the cloud from which the solar system formed. The existence of a confirmed stellar leaderboard, a list of the largest known stars, regularly updated as new observations and measurements arrive, reflects something important about the human relationship with scale. There is a specific type of wonder that comes from finding the extreme end of any distribution, from identifying the largest, the most distant, the most energetic, the most ancient. It is the same impulse that drove medieval explorers to seek the edges of maps, and that drives modern astronomers to push every survey to its detection limit. When we catalogue the largest stars, we are doing something more than gathering astronomical data. We are testing the limits of what the universe permits, finding where physical law draws its boundaries, and in the process learning something about the structure of physical reality. The Eddington limit is not just a constraint on stellar sizes, it is a window into the physics of radiation pressure and gravity. The pair instability threshold is not just a mass cutoff, it is a demonstration of quantum mechanics operating at astrophysical scales. The sizes of population 3 stars are not just large numbers. They are a consequence of the specific cooling physics available in a universe that had not yet been enriched by the first generation of stellar deaths. Every extreme object in this catalogue is teaching us something about fundamental physics. There is one last thing worth saying about the stars in this catalogue, and it is simple. The material they are made of, the hydrogen and helium in the outer envelopes, the carbon and oxygen and silicon and iron being forged in the cores, is the same material that you are made of, not in spirit or in metaphor, literally, physically, the same atoms. The carbon in your DNA and the carbon in the outer atmosphere of Betelgeuse are chemically identical. Carbon atoms do not carry any memory of the stellar core they were forged in, or the interstellar cloud they drifted through, or the protostellar disk they were incorporated into. But we can trace the path those atoms took, from the Big Bang's raw hydrogen through multiple generations of stellar birth and death, and supernova and drift and collapse, all the way to the molecular machinery inside cells on a small planet orbiting a modest yellow star. The largest stars in the universe are the most productive stops on that journey. They are the chemical factories that built the complexity needed for everything that came after. They are not a distant curiosity. They are a chapter in your own history. The question of what a hypothetical observer stationed on a planet in the same cluster as Stephenson 218 would experience deserves consideration. The Stephenson 2 cluster contains approximately 24 red supergiants in addition to the record-holding primary. A planet orbiting a star in that cluster, assuming it could maintain a stable orbit in such a dynamically active environment, would see a sky populated with objects that dwarf anything in our own night sky. The nearest cluster members, separated from each other by perhaps a few light years on average, would appear as brilliant red stars bright enough to be visible in daylight, bright enough to cast distinct coloured shadows at night. Stephenson 218 itself, even from several light years away, would be a disk of deep red light visible to the naked eye, not a point but a smear, an object with resolvable angular size. The combined illumination from the cluster's members would eliminate any true darkness from the sky. There would be no night in any familiar sense. The sky would have a permanent pale red glow from the cumulative light of dozens of supergiant companions, each one extraordinary by the standards of our solar neighbourhood, all of them ordinary by the standards of their own cluster. The study of stellar populations in nearby galaxies, accessible to detailed observation, provides a way to test stellar evolution models against samples that differ in metallicity and star formation history from the Milky Way. The Magellanic Clouds have lower metallicity than the Milky Way, meaning their massive stars lose mass more slowly and can potentially reach larger final masses before exploding. This prediction is testable. If lower metallicity allows more massive final explosions, the Magellanic Clouds should show a higher rate of the most energetic supernova types than the Milky Way. Several observed supernovae in the Magellanic Clouds have indeed shown properties consistent with more massive progenitors than typical Milky Way events. The supernova of 1987, SN 1987A, occurring in the Large Magellanic Cloud, and the closest supernova observed with modern instruments, produced a flood of neutrinos detected by observatories in Japan and North America, confirming the core collapse mechanism in direct observation for the first time. It showed that massive stars in lower metallicity environments died differently than those in the Milky Way, and it fundamentally changed our empirical understanding of how massive stellar deaths actually proceed. In the context of cosmic history, the universe is past its peak star formation period by a substantial margin. Star formation peaked roughly 10 billion years ago, when galaxies were young, rich with pristine gas, and colliding frequently with each other. In that era, the rate of new stars being born per unit volume of the universe was perhaps 10 to 20 times higher than it is today. Enormous galaxies blazing with ultraviolet radiation from thousands of newly formed massive stars dominated the early universe's landscape. As those stars died and their gas was consumed, enriched, and either locked into compact remnants or expelled from galaxies by feedback, the rate of new star formation declined. The universe today is forming stars at a fraction of its historical maximum. The era of the very largest stars, which require specific formation conditions involving abundant pristine gas and dense cluster environments, is declining accordingly. The monsters in this catalogue, the hypergiants and supergiants, are the last generation of a type that was more common when the universe was young. Each one is a window into the kind of stellar production the early universe engaged in routinely. The Hertzsprung-Russell diagram plots every measured star's luminosity against its surface temperature, and when you look at where the current catalogue of red supergiants and hypergiants sits on that diagram, you are looking at a specific corner of the parameter space that represents the last active phase of massive stellar evolution. Stars arrive at the red supergiant region from the left, from the hot, compact, luminous blue main sequence as they exhaust their hydrogen and expand. They stay in the red supergiant region for a relatively brief time compared to the main sequence lifetime, then either explode or, in rare cases, briefly shed enough material to return to the blue side of the diagram as compact hot objects before a final explosion. The duration of the red supergiant phase is one of the key uncertainties in stellar evolution theory. Some models predict longer times in the red region, others shorter. The observed number ratio of red supergiants to blue supergiants in different galaxies is one of the tests used to constrain these models, and current observations do not perfectly match any single theoretical prediction. The largest stars in this catalogue, the hypergiants at the extreme upper end of luminosity, live in a part of the Hertzsprung-Russell diagram that is so sparsely populated that statistical samples are very small, making it difficult to test evolutionary models quantitatively. Looking at the complete catalogue assembled over the course of this exploration, Sirius and its white dwarf companion, Rigel burning blue in medieval time, Betelgeuse convulsing at Orion's shoulder, Antares spreading its blood-red light across Scorpius, Mu Cephei glowing garnet in the northern sky, VV Cephei A with its blue companion plunging through its outer atmosphere every 20 years, the dust-hidden giants of Cygnus and Sagittarius, WOHG 64 behind its enormous Taurus in the Large Magellanic Cloud, and Stephenson 218 at the top, containing 10 billion suns in its volume, sitting at the wall that physics has built. What emerges is not a random collection of extreme objects, but a coherent picture of what happens when gravity, nuclear physics, and radiation pressure are pushed to their respective limits. Every star in this catalogue is exploring the boundaries of what these fundamental forces permit. Every one of them is temporary. Every one of them is, in the long view, a brief episode of extraordinary productivity in the ongoing project of transforming the universe from a simple hydrogen and helium soup into something complex enough to ask questions about itself. The concept of stellar death needs some qualification when applied to the most massive objects. For a normal star like our Sun, death in the sense of cessation of nuclear fusion is final and irreversible. The star becomes a white dwarf and cools indefinitely, never reigniting, never producing energy through fusion again. For the most massive stars, death describes something more like a catastrophic transformation. The outer layers are violently expelled, the core collapses into a neutron star or black hole, and the resulting objects continue to be active for billions of years in different ways. A neutron star powered by rotation and magnetic field energy, a pulsar, is in some sense a form of continued stellar activity, even if the energy source is completely different from fusion. A black hole accreting material from a companion star or from surrounding gas produces some of the most energetic per unit mass phenomena in the observable universe, with luminosities that can exceed those of the original star. In this sense, the death of a massive star does not remove it from the energetic inventory of the galaxy. It transforms it into a different kind of energetic object that may remain active for far longer than the original stellar lifetime. The compact remnant of a massive star explosion is a different machine running on different fuel, but it is still a machine, still contributing energy and radiation to the surrounding space, still interacting gravitationally and electromagnetically with everything nearby. The cosmic ray background that permeates the Milky Way, a continuous flux of high-energy particles moving through the galaxy at close to the speed of light, is primarily produced by supernova shockwaves. As the expanding blast wave from a supernova plows through the surrounding interstellar medium, it accelerates electrons, protons, and heavier nuclei to relativistic velocities through a process called Fermi acceleration. These accelerated particles then propagate throughout the galaxy, confined by magnetic fields that cause them to spiral along field lines rather than traveling in straight lines. When cosmic rays collide with interstellar hydrogen, they produce gamma rays detectable by space observatories, and they ionize the cold cores of molecular clouds that would otherwise be shielded from energetic photons. This ionization by cosmic rays is crucial for the chemistry of dense molecular clouds because it creates ion molecule reactions that produce complex organic molecules in the cold interiors of clouds too dense for ultraviolet light to penetrate. In this way, supernovae from massive stars are indirectly responsible for the complex organic chemistry that occurs in the cold cores of molecular clouds. the very same clouds from which the next generation of stars and planetary systems will form. The connection between stellar death and molecular complexity is direct, operating through the cosmic ray irradiation of cold gas by energetic particles accelerated at the remnants of previous stellar explosions. The question of what the largest star ever to have existed in our universe might have looked like, if such a thing could be answered, requires pushing through the physical limits discussed throughout this catalogue and into territory that is partly theoretical and partly extrapolation. If dark stars existed in the early universe and reached sizes of millions of solar radii, as some models predict, then the largest stellar object in history may have been larger than the typical distance between stars in the present-day Milky Way. An object whose diameter exceeded 4 light-years would span the distance between our Sun and Proxima Centauri, the nearest known star. From inside such an object, you could travel in a straight line for years at the speed of light without reaching the edge. The concept of a stellar surface would lose nearly all meaning at these scales. The object would not end. It would simply become increasingly thin and cool as you moved outward, eventually grading into something indistinguishable from an extremely dense interstellar cloud. Whether such objects ever existed is unknown and may be unknowable with current technology, but the physics allows for them under the right early universe conditions, and physics has a way of taking every permission it is given. Supernovae do more than scatter elements into the interstellar medium. They also inject kinetic energy, cosmic ray particles, and magnetic field structures that shape the physical state of the gas across large volumes. The cosmic rays accelerated at supernova remnant shockwaves are the primary source of the high-energy particle radiation that permeates the galactic disk. These cosmic rays, which are primarily protons and heavier atomic nuclei moving at close to the speed of light, collide with interstellar hydrogen and produce gamma rays detectable by space observatories. The ionization that cosmic rays drive in cold, dense molecular clouds is crucial for chemistry. It creates ion-molecule reactions that produce complex organic molecules in cloud interiors too, dense for ultraviolet light to penetrate. In this way, supernovae from massive stars are indirectly responsible for the complex organic chemistry that occurs in the cold cores of molecular clouds, which are the very same clouds from which the next generation of stars and planetary systems will form. The connection between stellar death and molecular complexity is direct. Every massive star that dies not only scatters heavy elements, but energizes the galaxy in ways that feed forward into all subsequent chemistry. The measurement of Stephenson 2-18's size is representative of the broader challenge of determining physical properties for very large, very distant, and heavily obscured stars. At 20,000 light-years and embedded in or near the dust of the galactic plane, Stephenson 2-18 cannot be observed directly at optical wavelengths. Every measurement of its properties requires infrared observations, careful correction for interstellar extinction, and physical modeling to extract temperature and luminosity from the observed spectral energy distribution. The distance itself carries an uncertainty that propagates into every derived quantity: size, luminosity, mass. A 10% error in the assumed distance produces a roughly 20% error in the derived luminosity and roughly 10% error in the derived radius. For Stephenson 2-18, distance estimates have ranged from about 5 to 7 kiloparsecs in different studies, which propagates into uncertainty in the size estimate of roughly 500 to 700 solar radii. The current best estimate of 2,150 solar radii could be 1, 700 or 2,600 depending on which distance and which atmospheric model you use. This is not a failure of science. It is the honest accounting of what we currently know and do not know about the most extreme stellar object in the confirmed catalogue. The observable universe contains something on the order of 2 trillion galaxies, each with hundreds of billions of stars, giving a total stellar population somewhere in the range of 10 to the 24th power. Among these, the fraction that qualify as red supergiants or hypergiants at any given moment is extremely small because these phases are brief. At any given time, roughly 1 in 50 million stars is a red supergiant. Applied to the full observable universe, that gives roughly 20 quadrillion red supergiants existing right now. Most are in distant galaxies, completely inaccessible to detailed study. The catalogue of named and measured hypergiants we have discussed tonight represents the tiny fraction close enough to our own galaxy that the light from them carries enough information to measure their sizes and temperatures with confidence. The actual population of extreme stars in the observable universe is incalculably vaster than the handful we have been able to name and characterize. This is not a problem to be solved. It is the shape of the universe, too large to fully inventory, too vast to fully map, perpetually offering more than any catalogue can capture. The interstellar medium that connects all the stars in this catalogue, the gas and dust that fills the spaces between them, is itself the product of billions of years of stellar mass loss and supernova enrichment. In the early universe, the interstellar medium was almost pure hydrogen and helium. After the first generation of massive stars lived and died, it contained trace amounts of heavier elements. After 10 billion years of successive generations of stars building up the inventory of heavy elements and distributing them through their deaths, the modern interstellar medium in the disk of the Milky Way contains roughly 2% by mass of elements heavier than helium. This fraction is tiny in absolute terms, but enormous in its consequences. It is the fraction that makes rocky planets possible. It is the fraction that allows molecular clouds to cool efficiently and form stars across the full range of masses from brown dwarfs to massive supergiants. It is the fraction that enables the formation of complex organic molecules in the cold cores of molecular clouds. It is the fraction that ultimately leads to the presence of carbon-based chemistry on at least one planet we know of, and almost certainly on many we have not yet characterized. The 2% is the accumulated output of all the stellar deaths that preceded us. The catalogue of the largest known stars is, at its core, a catalogue of physical limits being approached. Each entry represents a star that has grown to the maximum size its physics permits at the current moment in its evolution. Stephenson 218 at 150 solar radii sits near the Eddington ceiling for normal stellar evolution. W8G64, wrapped in its dust torus, is approaching the limit of coherence as its mass loss rate challenge mechanisms of stellar self-maintenance. Westerland Wonder 26 may be actively crossing the Eddington limit during certain phases of its life, held together by magnetic fields rather than by a straightforward radiation-gravity balance. Every one of these objects is an experiment at the boundary of what physics allows, and every observation of them adds to our understanding of where those boundaries actually lie. The universe's largest stars are not records to be broken. They are benchmarks for testing our understanding of the laws that govern everything. The question of why we catalogue these stars at all, why humans point their instruments at the most extreme objects in the galaxy and spend careers measuring their temperatures and sizes and mass loss rates, has a straightforward answer. These objects are the endpoints of the most consequential physical processes in the universe. The heavy elements that make planets rocky and chemistry complex were manufactured inside them. The shock waves that triggered the collapse of the molecular cloud that became our solar system came from something like them. The iron in your blood was forged in something exactly like them. When you measure a red hypergiant, you are not just collecting astronomical data. You are reading the instruction manual for how the universe made you. Every number in this catalogue is a chapter in that manual. Every red star glowing in the night sky is a page still being written. The story does not have an ending. It has a horizon, and the horizon keeps moving. And beyond it there is always something larger than what we have found. Something more extreme than what we have measured. Something the universe has been building in the dark since long before we were here to look for it. The surface of Betelgeuse, if you could somehow stand on it, would not look like a surface. It would look like a boiling ocean of gas stretching to every horizon, with enormous bright patches rising and falling over months-long cycles, with dark regions where cooler material has sunk back toward the interior, with streams of ejected material rising away overhead and vanishing into the blackness in between the star and whatever lies beyond it. The star would not look like a sphere from any internal perspective because its outer atmosphere is not a sphere. It is an irregular, turbulent, constantly changing volume of gas that occasionally develops enormous asymmetric bulges that change the star's apparent shape on timescales of months to years. This is what the largest stars actually are, not the clean spheres of textbook diagrams, not the featureless glowing balls of popular imagination. Turbulent, irregular, barely coherent structures of gas and radiation that happen to be large enough that their own gravity keeps pulling most of the material back before it escapes permanently. The smooth glowing sphere is a convenient fiction. The reality is much stranger, much more active, and much more beautiful. The scale of what exists in the universe does not conform to what human intuition considers reasonable. A star large enough to contain 10 billion suns in its volume, burning at temperatures that forge new elements in its core, shedding material continuously into surrounding space, sitting 20,000 light-years away and showing you light from before the last ice age ended. This is not an abstraction. It is a physical object in the real universe, governed by the same laws of physics that govern everything else. Its existence is not a mystery. It is a solution. The solution to what happens when gravity, nuclear physics, and radiation pressure interact at sufficient scale. The universe solves this equation billions of times across trillion galaxies and produces these objects as the answer. We are fortunate to live close enough to a few of them that we can measure them in detail, trace the physics of their interiors, and recognize in their composition the origins of our own. That recognition is one of the more remarkable things that has ever happened in a universe that has been running its experiments for nearly 14 billion years. The sky is not finished being discovered. The largest star in the catalogue today will almost certainly not be the largest star in the catalogue a generation from now. The catalogue itself is the work, and the work is ongoing, and anyone who looks up at the night sky is participating in it whether they know it or not. That is, in the end, what science is, looking up and asking what is actually there and not stopping until the answer arrives.